This is Lab 6, my magnetic molasses lab for Physics 1212. So as an introduction, the purpose of this lab was to gather experimental data and observe how a magnet falling through an aluminum foil tube would act. After that, we would analyze and apply Faraday's law using the recorded measurements that we got after testing each magnet falling through 5 times. And from there, we would develop a computational model that would illustrate the law in this specific setup using WebPython. So the fundamental and models and principles used in this lab were the Biot-Savart law, which describes the magnetic field generated by a constant electric current. That is seen in the picture to the right. You can also see this in Faraday's law, which is a change in the magnetic flux that can generate EMF. That is seen on the picture in the left. And then we also used the magnetic field of a dipole, which was distinguished by 2 opposing poles using a bar magnet at north and south. We also used Ohm's law and Newton's second and third law. So as a brief preview of the main result, the computational time came out to 3.87 seconds with the WebPython computing, but the experimental time, which was the average of our 5 trials, was 0.768 seconds. So as you can see, a very vast difference. So the details of this lab, the filming was done with an iPhone 16 and the timing for each fall was extracted from there. We used WebPython for the rest of the experiment, and there was 2 assumptions that had to be made for this experiment, which was that the bar magnets would act as a magnetic dipole and that air resistance was negligible. So for the system and surrounding, the bar magnet, the tube, top of the table acted as the system, and everything else around the lab acted as the surroundings. In the initial condition for the magnet properties, the mass was measured as 0.025 kilograms, and the mu mag was 5.1135 area times meter squared. This was computed in the last lab. The tube dimensions for the length, we got 0.46 meters, the width as 0.005 meters, and the inner radius as 0.02 meters. And a picture on the right to show one of the trials we did. So the results, we had 5 trials, each with the change in time in seconds. One was 0.82, the second was 0.71, the third was 0.75, the fourth was 0.72, and then finally, trial 5 was 0.84. The average change in time was 0.768 seconds. And the potential errors that we noted were that there could have been external magnetic influences, like nearby magnetic objects that might exert additional forces on the system, or the fact that we neglected air resistance because this model does not account for drag from the surrounding area. We also didn't check for possible path deviation, since the magnet may not travel in a perfectly straight line inside the tube and would sometimes hit the edges. This is a video of one of our trials. So for the coding model, this was my code. It was in all these steps as shown below, and this was the results that we got. That was the velocity versus time graph that was created, and to the left is just a visual representation of the bar magnet falling through the tube. So the time in the tube in seconds was 3.12 seconds computationally. So for the what if first question, a lower resistance would increase the induced current and thereby enhance the magnetic field that opposes the magnet's descent under gravity. And for the second what if question, a reduced number of loops would mean that there's weaker opposing magnetic forces, and this would allow the magnet to fall more rapidly. That is lab 5. Thank you.